For number 20, they want us to predict whether the sulfide ion or the calcium ion will be smaller. So here I've written some information about them. So sulfur has 16 protons, and it will have 18 electrons when it has a -2 charge. Calcium has 20 protons and will have 18 electrons when it has a +2 charge. So these are isoelectronic with each other, same electrons. And so it turns out that because calcium has a greater positive charge at the center, it's able to better pull in electrons. It's a greater Z effective on the electrons. And so, since it's squeezing those electrons in, it will be smaller. So the answer here is D. In number 22, we're looking at an electron moving toward a proton. We're trying to figure out whether the energy increases or decreases, and how that affects the stability. So we know that a negative charge interacting with a positive charge is going to be favorable. And so as this gets closer, and closer and closer and closer, the distance decreases. And that means overall the magnitude of our energy is going to increase. And so when I say that, I just mean we're going to get a bigger and bigger negative number as the distance decreases. And so that means that our internal energy is going to decrease. And that energy is going to flow out of the system because maybe at first, maybe our potential energy had a value of like -5. And then as the system changes, maybe it goes to -10. And so that means that energy flows out of the system. And remember, molecules and particles like to be chill, like to be at a lower energy that's a more stable position, making C the correct answer. For number 23, they're asking how many electrons in an atom can have the following quantum numbers. Then they give us a value for N, L, and M sub L. And so when we know all three of these things, that's when we're describing a specific orbital. And we know that in a given orbital, we can fit 2 electrons. And so the correct answer here is just C. And it doesn't even matter what the values on those are. Just that we know 3 of them means that we are only talking about one specific orbital, or one box or one line in our arrow diagrams. Here's number 24, and we're just going to identify what we call different regions on the periodic table. And so here we have our S block, our P block, our D block. We don't talk about this as much, but we have our F block here. And so that just tells us where the outermost electron is going to reside. Number 25, we are trying to figure out which series of quantum numbers can describe the lowest energy electron in the ground state of potassium. And so what I've done here is gone through and converted the N and the L values into how we more commonly write out the subshells, 1s, etc. And what I see right away, before I even consider the energies of these, that D is not going to be a possible set of quantum numbers. We need L to be less than N. Here they're equal. There's no such thing as a 1p orbital. Okay, so then we're thinking about the energy. We want the lowest energy electron. And so that lowest energy electron is going to be A. It's going to be the 1s electron. It's closest to the nucleus, able to interact most strongly. Here in number 26, they ask what the maximum number of electrons in the ground state of cobalt can have a quantum number m sub L equals 0. And so when m sub L equals 0, this can correspond to an S, a P, a D. Could be one of the orbitals for any of these. Okay. So in the case of an S subshell, we know then that L is equal to 0. So m sub L is equal to only 0. And we know for a p orbital, when L is equal to 1, m sub L could either be -1, 0, or 1. And for a d orbital, L is equal to 2, so m sub L has 5 possible options. And so what we're going to do is just draw out the arrows and then go through and look to see when m sub L is 0 and just count our electrons. And so whenever they have a question where they ask me to count electrons, I always like to go through and draw all of the arrows, even though it can be a little bit of a nuisance. Okay, so we're going to have our 1s, 2s, 2p, 3s, 3p, 4s, and then our 3d, we have 7. Okay. So now I'm just going to go through and say, well, for my s electrons, those are definitely m sub L equals 0 because there's no other option. And then for the P and the D subshells, I'm just going to say, well, one of these boxes is going to correspond to an m sub L equals 0. Doesn't matter which one here because they're all the same. But it does matter here in this D, the 3D subshell. That's because sometimes it has one electron, sometimes there's 2 electrons in the orbital. So in the problem it says we want to have the maximum number of electrons, and so we want to consider one of them with 2. So then we just count 2, 4, 6, 8, 10, 12, 14 electrons could possibly have an m sub L equals 0. In number 27, they give us 5 sets of quantum numbers. And they want us to pick which of the electrons require the most energy to remove. And so we know that when we go to remove an electron, we start by removing the ones that are furthest away. And so, since A and B have an n equals 4, those would be easier to remove than the ones that have n equals 3. So we can cross those out. And then once we have electrons that have the same n, the electron that is lowest energy then will be hardest to remove. So the one that is lowest energy will be E, because this is our 3s electron. And we'll remove a 3d and a 3p before we move on and remove a 3s electron. Okay, in number 28, they go ahead and say that there's a burst of gamma rays from a neutron star in space. Radiation has a frequency of 1 times 10 to the 19 hertz, and the burst released 1 times 10 to the 44 joules of energy. I want us to figure out how many moles of photons of gamma radiation were released during this burst. Okay, it's kind of a lot of information. And so I'm going to start by just picking the equation that relates energy and frequency to each other. And that is this E equals h nu equation. And that is on the data sheet along with the constants. And so h is Planck's constant at 6.626 times 10 to the negative 4 joules times second. And then they tell us what nu is, or the frequency, in the problem. And hertz is just the same thing as per second, or seconds to the minus 1. So, what I like to do then is to figure out the energy of one photon, and then figure out how many photons we're working with. So when I plug into this equation, the energy that will pop out will have units of joules per one photon. Okay. So you can set this up. Say E equals 6.626 times 10 to the negative 34 joules times seconds times 1 times 10 to the 19th seconds to the minus 1. I prefer to write seconds to the minus 1 instead of hertz, just because then I can see how my units cancel. And so my energy for one photon is going to be 6.626 times 10 to the 15th joules per photon. Okay. And so now that I know how much energy one photon contributes, I can go ahead and figure out how many photons would make up the entire pulse, or the entire burst. And then if I know how many photons I have, I can go ahead and just use Avogadro's number to convert to moles. So, I'm going to go ahead and start with the given energy, which is the 1 times 10 to the 44 joules. And then I can use that energy I just solved for as a conversion factor. And so I can say one photon, and I need photons on top so that I can cancel joules. So in one photon, I have 6.626 times 10, oh, this should be negative 15th, sorry, negative 15th joules. And so at this point, joules cancels out, and we would solve for how many photons we have. And so once we know that, we can go ahead and say, well, there's going to be Avogadro's number of photons in 1 mole. So our units will cancel out. Joules cancel, photons cancel, and we're left with the desired unit of moles. And then we go ahead and do the computation. And that value ends up being 2.5 times 10 to the 34 moles of photons, or answer choice B. This is a lot of photons, which makes sense though because that was a lot of energy in the pulse. Okay, and number 29, they're asking what the maximum wavelength of a photon required to ionize a hydrogen atom that initially had an electron in n=3 shell. Okay. So here I have the Rydberg equation, where we look at kind of how changing the shells will change the energy. So we know that one of our n values is equal to 3. They don't tell us the other one. And so what you have to realize is that when we ionize something, it means we're removing the electron. And so we can go ahead and say that our final value for n is going to be kind of like infinity. We're taking it to a shell that's so far away, the distance is kind of infinite. Okay. So if we go ahead and write this out, so our initial state is 3, we can solve for the energy. So we can go ahead and say that the energy associated with this transition is equal to Ry, which is 2.18 times 10 to the negative 18th joules. Oh shoot, I'm going to run out of room. Sorry. 1 second. Okay, so we have energy is equal to Ry, which you can find on the data sheet, joules, times 1 over our initial position. So 3 squared minus 1 over our final position. And I had a slight error up above, but that version is indeed correct. And you can see that on the data sheet. Okay. And so if you divide by a really, really big number, you get smaller and smaller and smaller and smaller values until it seems insignificant. And so what we're going to do is go ahead and say that this is just 0. And that makes solving for the energy a lot easier. And we can see that this energy is 2.42 times 10 to the negative 19th joules. So that's how much energy we would have to put in to move one photon from the third shell out of the atom. And so, that's not really what they're asking us for though, right? They're asking us for wavelength. And so, we're going to have to do a second calculation now, where we convert the energy of our photon required and convert it to wavelength. So E equals hc over lambda. Okay. So I'm going to go ahead and erase this calculation. Okay. So we're going to use that E equals hc over lambda equation. And these constants are on the data sheet, but we have Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. We have c, which is the speed of light, which is 3 times 10 to the 8 meters per second. So we can take the energy that we need and set it equal to hc over lambda. And then we can solve for lambda. And we get answer choice C. 821 times 10 to the minus 7th meters, which is the same as saying 821 nanometers. Okay, so that would be like an infrared photon. Okay, here for number 30, we have two ions, sodium and fluoride, and we have to pick what's true. And so looking at the periodic table, we can see that both of these ions have a neon core for their electron configuration. So these are isoelectronic, they have the same electrons, making the first statement true. To figure out how many neutrons each of these elements have, we're going to have to use their mass number combined with their atomic number. So, we know that our mass number is protons plus neutrons. And so we can do, for sodium, 21, our given mass number, is going to be equal to the atomic number, for sodium 11, plus our number of neutrons. We can see then that we're going to have 10 neutrons. For the fluorine 19, we'll have 19 is equal to its atomic number, which is 9, plus neutrons. And so we can again see that this would have 10 neutrons. So the second option is also correct. The third statement says sodium ion and fluoride ion are both cations, and that is false. Fluoride is an anion, so it can't be a cation. Cations have to have positive charges. The T in cation is kind of like a plus. That helps us remember. And then statement 4 says they have different number of protons, and this is true. Right, when we looked on the periodic table, we found the number of protons each one has, and that's what makes sodium sodium and fluoride fluoride, is the number of protons that they have. If they had the same number of protons, it would be the same element. So answer choice C is correct. For question 32, trying to figure out how many moles of sucrose are in a 1 liter can of soda given a density. So when we use density, we're going to have grams, but we're trying to figure out moles. whenever we have kind of moving from the region of mass to moles, we need that molecular weight. And so I've gone ahead and already written that down. To figure this out, you would just take the number of carbons we have, so 12, times the mass of each carbon, which you can get from the periodic table. It was about 12 grams per mole. Then you do the same for hydrogen and oxygen and just add all of those up. Okay, so we know that density is equal to mass over volume, and we can use this as a conversion factor between volume and mass. So I'm going to go ahead and look at my volume, look at my density, and check my units. I can see that there are different units. And so I'm going to go ahead and say that my 1 liter is instead the same as 1,000 milliliters. And by doing that, I can go ahead and say that for every 1 milliliter, I'm going to have 0.867 grams. So I can use that density as a conversion factor. And then I can use my molecular weight as a conversion factor. I can put grams on bottom, moles on top, and say that for every 1 mole of sucrose, it weighs 342.3 grams. So then at this point my milliliters cancel, my grams cancel, and I'm left with moles. And I can see that this ends up being 2.53 moles. And from there you could even figure out how many atoms of sucrose are, or molecules of sucrose are present in a liter of soda. Okay. So that's the last problem for this practice exam. I hope that you all are feeling confident, getting good practice in, you know, not just watching me do it, right, but having done it already, having your pen and calculator going. And so you all have been doing lots of hard work, and this is your chance to show us. So, keep up the hard work. You all are doing great, and we'll talk to you soon.